Hey everyone, welcome to another deep dive. Today we're exploring the world of Ilya Frank.
A Nobel Prize winner.
Exactly. He's a physicist, but you know, I always wonder about the stories behind these big names in science. Like, who were they? Where did they come from?
It's easy to forget they were real people.
Yeah, not just like walking equations. So today we're going beyond the Nobel Prize and diving deep into Ilya Frank's life.
Starting with, well, you gotta start somewhere, family.
Oh, his family is fascinating. Not just scientists, but right in the middle of some major historical stuff, too. Think about it. His dad's a mathematician, but also involved in revolutionary movements.
Oh, and his mom.
A physician. Completely different background, even religiously.
Wow. Talk about some intense family dinners. I read his father even got kicked out of Moscow University for all that revolutionary business.
That's right. And get this, Frank's uncle, Semyon Frank, he was a big deal philosopher, but guess what?
What?
Expelled from the entire USSR in 1922.
No way. Talk about a turbulent time to be alive. It makes you think how that kind of upbringing shaped Frank. Absolutely. Especially since he ends up working in, well, let's be honest, a pretty politically charged field.
Yeah.
Nuclear physics.
True. But it wasn't just politics in the family, right? Science was in the blood, too.
Oh, yeah. His brother, Gleb, became a pretty famous biophysicist himself.
So scientific curiosity, it was a family affair. I wonder if they ever, had those sibling rivalry moments in the lab.
Maybe. But speaking of labs, let's talk about Frank's early career. Starts working with this leading Soviet physicist, Sergei Vavilov, during his second year at Moscow State University.
I'm always curious about those mentor relationships, how they shape someone's path. What was it like between them?
It was huge for Frank. Vavilov, he wasn't just a supervisor, more like a mentor and collaborator.
Right.
They were diving into luminescence, light stuff at the State Optical Institute, that's in Leningrad.
And that research.
It became the basis of Frank's whole doctoral dissertation. Imagine that, working in the lab, figuring out the secrets of light, alongside someone who totally believes in you.
I bet that sparks a passion for science, for sure.
No doubt. But when most people think of Frank, they think of one thing, Cherenkov radiation.
Okay, gotta admit, that sounds a bit intimidating. What exactly is that? Break it down for us.
Picture this. A particle, say an electron, zipping through water. But here's the catch. It's going faster than light can in water.
Wait, hold on. Doesn't Einstein say nothing goes faster than light?
Right. But he means light in a vacuum, like outer space. In something like water, light slows down. And a particle, it can actually outrun it.
Okay, so what happens when a particle breaks that speed limit in water?
It's like a sonic boom, but with light. Creates this optical shock wave, and that, my friend, is Cherenkov radiation. It actually looks like a faint blue glow. Pavel Cherenkov, another Soviet physicist, he saw this weird glow back in the 1930s, but no one could explain it.
And that's where Ilya Frank steps in.
Not alone. He teams up with Igor Tamm, and together, they crack the case.
A scientific dynamic duo.
You got it. They developed this whole theory to explain how particles can move faster than light in a medium and how that creates this disturbance in the electromagnetic field, which we see as Cherenkov radiation. Revolutionary stuff.
Hold on. Disturbance in the electromagnetic field. Can we get a visual on that? Help us picture it.
Think of it like a speedboat on a lake. The faster it goes, the bigger the waves, right? Well, the speedboat is our tiny charged particle, the lake is our water or whatever medium it's in, and the waves, those are the light waves, the Cherenkov radiation.
Ah, so it's not breaking the ultimate speed limit, just causing a ripple effect because it's going faster than light can in that specific stuff.
Exactly. And get this, they even came up with a formula. The Frank-Tamm formula. It lets scientists actually calculate the energy given off by this radiation, like a speedometer for super-fast particles.
So we went from a spooky blue glow in a lab to a formula that can measure the energy of these particles. That's wild.
Yeah.
How did this discovery change things in physics and, beyond?
That's where things get really cool. But first, just gotta give props to Frank and Tamm. Two brilliant minds coming together, pushing each other to understand this crazy universe.
Absolutely. It reminds us that science is often a team sport.
Right, totally. So you want to hear how their breakthrough went from theory to real-world stuff.
Lay it on me. Did this just stay in the physics lab, Or did it have a bigger impact?
Oh, it went way beyond the lab. It changed how we study the universe, especially the tiny stuff, the subatomic world. Remember, this was around the time when nuclear fission was a hot topic, the dawn of the nuclear age, you could say.
And scientists needed tools to figure out how these high-speed particles from nuclear reactions, how they worked.
Exactly. Frank and Tamm, their work with Cherenkov radiation, it gave scientists a brand new way to study the atom.
Like a new microscope into the heart of matter.
You got it. And not just for nuclear reactions either. This discovery had applications everywhere, from medicine to energy. In fact, one of the biggest uses. A medical imaging technique you've probably heard of, the PE scan.
Wait, are you serious? PE scans use Cherenkov radiation. I thought those were all about X-rays or something.
It's a bit of physics magic, for sure. They inject a tiny bit of radioactive tracer into the body. This tracer releases positrons, which are like the antimatter version of electrons.
Antimatter. That sounds like something out of Star Trek.
It might sound futuristic, but it's happening in hospitals right now. These positrons, when they meet regular electrons, they annihilate each other, releasing gamma rays. And those gamma rays, as they go through the PT scanner, they can create Cherenkov light.
So doctors are using tiny explosions of antimatter and light to see inside us. That's insane.
It just goes to show how a physics concept can turn into a life-saving medical tool. And that's not all Cherenkov radiation does for medicine. It's also being used in radiation therapy to target and destroy cancer cells super precisely so it doesn't hurt the healthy cells around them.
Wow. Just wow. From a weird blue glow to fighting cancer. That's an incredible journey for a scientific discovery. But it wasn't all medical breakthroughs for Frank, right? Didn't you mention nuclear reactors too?
That's right. And that part of his work, well, it brings up a whole new set of questions about science, politics, and the world during the Cold War.
Okay, now we're getting into some seriously interesting territory. The Cold War, nuclear technology, the power of the atom. Can't wait to hear more about this.
Yeah, Frank working on nuclear reactors, it adds a whole other dimension to his story. Think about it. The Cold War is going on and nuclear technology. It's right at the center of that global chess match. Super secretive, lots of political pressure, and then there's that fear, of total nuclear war. Makes you wonder how scientists like Frank dealt with all that.
It's got to be tough, right? Balancing your scientific work with the demands of the Soviet system, especially in a field like that. Did Frank ever, feel conflicted about his research, like knowing it could be used for good or for, something really bad?
It's a question that still comes up. Some folks say Frank was totally dedicated to the Soviet Union, believed that nuclear technology could really help society, help his country progress, maybe even the whole world.
But others might say he had to make compromises. Be careful not to step on any toes politically so he could protect himself and his research.
Yeah, it's hard to judge, We weren't there in that pressure cooker. What we do know is that Frank's research on reactors was really important for the Soviets' nuclear program. He was focused on something called neutron thermalization. That's key for controlling those nuclear reactions.
Okay, neutron thermalization. Sounds kind of sci-fi, got to be honest.
Yeah.
What's that in plain English? What was Frank trying to do?
Not that complicated, really. Basically, it's about slowing down neutrons. You need to do that to control the chain reactions that happen inside a reactor. Like, imagine you're trying to tame all that energy in an atom. You need to put the brakes on those neutrons that are zipping around, causing all the reactions. Kind of like speed bumps for atoms.
So Frank was all about harnessing the power of the atom, but doing it safely. Right. Amazing to think he was figuring this stuff out when nuclear tech was brand new.
His work was a big deal, even if a lot of it was top secret back then. He eventually became the director of the Laboratory of Neutron Physics. That's at the Joint Institute for Nuclear Research, a huge international place. There, he really focused on something called neutron spectroscopy.
Now, neutron spectroscopy, is that connected to his Cherenkov radiation work? I feel like I'm seeing some links between all this research.
You're getting it. Neutron spectroscopy, kind of like Cherenkov radiation, it lets scientists study how materials work, at the atomic level. Imagine shining a really special light on something and seeing how the neutrons react to it. This has uses all over, from figuring out how materials work to understanding stuff in biology.
So Frank's research goes way beyond physics, impacting all these different fields.
And even with all the politics and secrecy, Frank's contributions got recognized worldwide. He won the Nobel Prize in Physics in 1958, shared it with Pavel Cherenkov, who first saw that weird blue glow, and of course, Igor Tamm.
It's cool how the Nobel Prize, this huge honor, it goes beyond politics, right?
Yeah.
It's like recognizing amazing science no matter where someone's from.
Totally. Science should be a global thing, right? People working together to understand the universe. Frank definitely deserved that recognition. Especially his work with Tamm, that was a textbook example of how great teamwork can lead to amazing breakthroughs.
You talked about how they developed that groundbreaking theory for Cherenkov radiation. What was it like for them to actually work together? Was it like a teacher-student thing or more like equals brainstorming?
From what I've read, they really respected each other and loved science. Tam was a bit older, more experienced, so maybe he was a bit of a mentor. But it sounds like they were pretty equal, both contributing a lot to that Nobel Prize winning work.
Their story shows that, these big scientific discoveries, they don't usually come from one lone genius working alone. It's about collaboration, about different minds working together to solve a problem. That makes it even more impressive, right? To do something revolutionary, you need to communicate, respect each other's ideas, and build on what everyone's thinking.
Exactly. They were a perfect pair. Frank was the theoretical physics expert, while Tam was a math whiz, the one who could turn those ideas into equations, into that elegant explanation for Cherenkov radiation.
And to think it all started with a weird blue glow in a lab. It's like you never know where a simple observation might lead. But let's shift gears a bit. We've been talking a lot about Frank and particle physics, but he also did a lot with nuclear reactors. That's got to be a whole different ball game, politically and ethically.
Oh, yeah, for sure. And this is where things get even more interesting, especially when we think about Frank's legacy today. In a world where nuclear technology is still such a big deal and so controversial, his work raises some really important questions about science, about its role in society, and about the responsibility that comes with pushing the boundaries of what we know.
We're getting into some big ideas now.
Yeah.
The ethics of science, right? On one hand, there's the potential for amazing things like medical breakthroughs and clean energy. But then there's the dark side, the nuclear weapons, the dangers of radiation.
It's complicated. We admire Frank's scientific achievements, but we can't ignore the ethical side of it all. How do you balance the pursuit of knowledge with the potential for both good and bad outcomes? That's a question that's still relevant today, maybe even more so than back then.
That's deep. It reminds us that science is about more than just equations and experiments. It's about how our discoveries affect the world and making sure we use that knowledge responsibly. But let's not get too philosophical just yet. We've only scratched the surface of Frank's work and how it's used today.
Right. We've talked about his childhood, all the craziness going on back then, and his amazing work with Cherenkov radiation and reactors. But there's more. In our last part, we'll look at how Frank's research is still being used today in fields like medicine, energy, and even materials science. Crazy, right?
It blows my mind that someone working in the middle of the Cold War could still be shaping our world today. So stick around. We'll be back to wrap up this deep dive into the incredible legacy of Ilya Frank. And we're back, still diving deep into the world of Ilya Frank. Amazing to think how his work from back in the Cold War is still so relevant today.
Yeah, it really makes you think, doesn't it, about how science just keeps moving forward.
Before the break, we were getting into some pretty heavy stuff, the ethics of scientific discoveries, especially in a field like nuclear physics, where there's so much, potential for both good and bad.
For sure. But for now, let's focus on the good stuff. How Frank's work is actually helping people today.
Okay, color me intrigued. Last we left off, we were in the realm of particle physics. How do we jump from subatomic particles to, hospitals and healthcare?
It all comes back to Cherenkov radiation. Remember that blue glow we talked about?
Yeah.
Particles moving faster than light in certain materials?
Yeah, I remember. Pretty wild stuff.
Well, that plays a key role in a technology you've probably heard of, PET scans.
Wait, hold on. PET scans use Cherenkov radiation. Seriously, I always thought those were all about X-rays or something like that.
It's a little bit of nuclear physics magic, I guess you could say.
Yeah.
They start by injecting a tiny bit of a radioactive tracer into the body. This tracer releases positrons.
Positrons. Okay, now we're getting really sci-fi.
They're the antimatter version of electrons, the opposite.
Antimatter. Okay, now I am officially lost.
It might sound like Star Trek, but I assure you it's happening in hospitals every day. So these positrons, when they bump into regular electrons in your body, they annihilate each other. Gone. Poof.
Okay, so far this sounds more like a superhero movie than a medical procedure.
But when they annihilate each other, they release energy in the form of gamma rays. And when those gamma rays go through the PT scanner, they can actually create Cherenkov light, which the scanner can detect.
So hold on. Doctors are basically using tiny explosions of antimatter and light to see what's happening inside us.
That's one way to put it. It's amazing, right? And it just goes to show how something discovered in a physics lab can lead to incredible medical advancements. And the story doesn't end there. Cherenkov radiation is also being used in radiation therapy to very precisely target and destroy cancer cells.
Wow, that's amazing. So they're using it to fight cancer too. So we've got diagnosing medical conditions and fighting cancer. What else can it do?
Let's talk energy. Frank's work on nuclear reactors still very much relevant today, especially with all the talk about finding cleaner, safer energy sources.
You mentioned his work on, what was it, neutron thermalization, slowing down those neutrons to control the reactions. Is that still important for reactors today?
Absolutely. Researchers are developing new and improved nuclear reactors that produce less radioactive waste. And guess what? Cherenkov radiation is playing a role in making sure these reactors are safe and running properly.
So they're using light to monitor nuclear reactors. How does that even work?
By carefully analyzing the light. The intensity and even the color of the Cherenkov light coming from the reactor core can tell scientists exactly what's going on inside. It's like a built-in alarm system that uses light to warn them of any potential problems. Pretty cool, huh?
It's mind-blowing to think that something discovered in a basic physics experiment can be used to monitor something as complex as a nuclear reactor.
And that's not all. We're also using Cherenkov radiation in materials science to study the properties of different materials at the atomic and molecular level. Imagine using this special light to figure out the structure of crystals or even design brand new materials with specific properties. The possibilities are endless.
This is making me realize just how connected different areas of science really are. A discovery in particle physics can have applications in medicine, energy, and now materials science. It's like knowledge just ripples outward, influencing everything.
Exactly. It shows how important fundamental research is. You never know what amazing applications a new discovery might have down the road. And it all goes back to pioneers like Ilya Frank, who really paved the way for all of this.
It's been such an incredible journey exploring Frank's life and work. We've seen how his childhood, with all the political turmoil back then, influenced him, how his brilliance and teamwork led to a Nobel Prize, and how his discoveries are still making a difference in the world today.
It's a story about the power of curiosity, collaboration, and the amazing potential of science to shape our world for the better.
I couldn't have said it better myself. Thanks for joining us on this deep dive into the fascinating world of Ilya Frank. Until next time, keep asking questions, stay curious, and never stop exploring.